All right, so label this 0 to 360 notes because we're going to allow our angles to go out, our rotation angles to go out of quadrant 1, out of quadrant 2, and into quadrant 3, or even into quadrant 4, our rotations in these notes, okay? First of all, TA questions. We're going to be given the radius and the rotation angle, and we have to find the coordinates. That means both the X and the Y, making sure that we have the correct sign, S-I-G-N. Watch out for that. So we have a radius here of 30 and a rotation of 160. So remember that rotation is counterclockwise and it's 160 degrees from the positive x-axis. So there's 90, 160 then would be in quadrant 2. There's my 160-degree rotation. And then I've got a point on the end of that, and I'm going to say that's 30 away from the origin. So you're thinking of having this circle with radius of 30, and the angle of rotation is 160. So we're trying to find the coordinates of that point. So we need to know how far over it is, call that X, and how high up that is, call that Y. Let's target finding Y first. If we target finding Y first, we want this angle to use. And that angle is my reference angle. And my reference angle would be 20 degrees. So I know that the sine of 20 degrees is equal to the opposite, which is Y over 30. I chose sine because I have the 30 and I want the Y. I have the opposite and I want the hypotenuse. That means I'm going to choose sine. If I multiply both sides by 30 then, using good algebra, I will get Y isolated. Y is 30 times the sine of 20. Make sure you're in degree mode. And estimate that. Y is about 10.3, let's say, to tenths. Now you got to make a decision though on the SIGN. And I'm going to say that's positive because I'm in quadrant 1. I'm going to go up 10.3 for my Y coordinate. For my X coordinate, that's this distance right here. And if I want that and I have the hypotenuse, I'm going to use CA. The cosine of 20 degrees is X over 30. I have the adjacent and I want the adjacent, I have the hypotenuse. I'm going to multiply both sides by 30. And I know that X is, and so in degree mode, I'm doing 30 times the cosine of 20. And I get about 28.2, right? But that isn't my X because I have to choose the correct sign. My X in quadrant 2 is negative. So I have to stick this negative on that X to give the coordinates of my point correctly, which would be negative 28.2, comma 10.3. I want to put that in a box. Negative 28.2, comma 10.3. Always double check that your reference point ends in the correct quadrant. This is quadrant 2, and that's right. X is negative, Y is positive. All right, that's going to be my double check. For part B then, we want to draw a 240-degree rotation. What quadrant would that be in? We'd have to go 180, and then we'd have to go another 60 degrees to get to 240. 180 plus another 60. So my reference triangle looks like this. I'm going to highlight that reference triangle in yellow. And let's see, my Y coordinate here, my X coordinate here. This is my right angle right here. And 60 degrees is my reference angle. I'm at 240 on my rotation, but 60 degrees is my reference. Now, how did I get from 240 to 60? I would take my quadrant 3 rotation, 240, subtract 180 degrees, and that gives me my reference. Rotation minus 180 degrees gives me my reference here. It's not something to like memorize, but it's something to note what's going on there, all right? Just kind of notice. Use the geometry to get your reference angle. Don't memorize things, but you're 60 degrees beyond 180 in rotation. So if I want y, that's my opposite, and I have my hypotenuse, 15. Circle with radius 15. Okay, so if I want my y, I have my opposite, or I have my hypotenuse, I want my opposite, so it's the sine of 60 degrees is equal to y over 15. I'm going to multiply both sides by 15 again in this case. I'm not going to have any tricky algebra to do. It's just 15 times the sine of 60. And I get my y to be really 13.0 when I round it. 13.0. It's 12.99. So that's what I'm going to use is 13. But wait, my sign. I'm in quadrant 3. Y is negative. My sign is going to have to be made negative. So for the coordinates of that point right there, I know my y is going to be negative 13, about 0.0, let's call it, because I rounded. And then for my x, that's the adjacent, and I have the hypotenuse. So it's the cosine of 60 degrees is equal to x over 15. 15 times the cosine of 60. Hey, wait, I know the cosine of 60. The cosine of 60, when I type it into my calculator, the cosine of 60 is 1/2. So this is exactly 7.5. But I have to make it negative because I have to pay attention to the sign. I'm in quadrant 3, and my x coordinate is negative 7.5. So the coordinates at that point I'll put in a box is negative 7.5, negative 13.0. In summary, for both of these problems, we found that the sine of 20 degrees was y, 10.3 over 30. We found the cosine of 20 degrees is 28.2 over 30. And we'd know that the tangent of 20 degrees then would be 10.3. It'd be the y, 10.3 over the x, 28.2. Remember that sine is going to be defined as your y over your r, while cosine is your x over your r, and tangent is your y over your x. So that's a summary of my trig ratios right here. Now you might be asking yourself, how come I didn't put the negative on the 28.2? And that's because I'm using my reference angle, and reference angles are in quadrant 1. So all of these ratios are positive if we're in quadrant 1. None of them are going to be negative ratios. A summary of my trig ratios for problem part B would be that I have the sine of this 60 degrees is equal to y, which is, y was right here, 13 over 15. The cosine of 60 degrees is my x, 7.5 over 15. And I know that the tangent of 60 degrees is equal to y over x. So that would be 13 over 7.5. And if I check these in my calculator, I'll see that to be true. Now, if I decide to use the rotation angle instead, the sine of 240 degrees is actually going to be negative 13 over 15. And the cosine of 240 degrees will actually be negative 7.5 over 15. And the tangent of 240 degrees will be negative 13 over negative 7.5, or 13 over 7.5. If I'm going to use that quadrant 3 rotation, well, then my sine and my cosine will be negative ratios. My tangent will be positive. For part B, I want to find TB. I'm finding the missing rotation angle and sketching the angle and labeling the sides of the reference triangle. So really what I'm trying to do is solve this trig equation. What the sine of theta is 4/5, but they tell me something about the rotation. The rotation is in quadrant 1. So when I draw a picture of it, I want to draw a rotation where the y coordinate is 4 and the radius is 5. So a circle with radius 5, okay? And then the y coordinate is almost the same as that 5. Okay, so there's the 5. and there's the 4. There's my rotation of theta. So when I draw an accurate picture of theta, I want to make sure that I kind of move that reference point up so that this leg is nearly as long, only one less than that hypotenuse. And that will help me like know what my sides of my reference triangle are. According to Pythagorean triples, this side would be 3. So now I've sketched the angle and I've labeled all the sides of the reference triangle. This is my X, that's my Y, and this right here is my R. 5 is my R. So I've sketched a picture of the angle, I've labeled the sides. Now the only thing to do is to find the missing rotation angle. So since what I was given was the 5 and the 4, and this is opposite the angle, and this is the hypotenuse, I'm going to use the sine of theta is equal to 4 over 5 to solve for theta. Theta is the inverse sine of 4 over 5. So I type into my calculator second sine, 4 divided by 5, and I get about 53 degrees to the nearest degree. And I've solved the problem for how big theta is. That rotation is about 53, which looks good to the picture too. So it kind of checks out. Because I drew my picture to scale, I can check my picture to scale. Now I have to be very careful because on the next problem, my theta is in 4 and my cosine is x over r. My x is 4, my r is 5, but my theta is in 4. So I need to rotate this so that the terminal side ends in quadrant 4. And I need my x to be nearly the same as long as my hypotenuse, which is 5. So this is 5, this is 4. Now I want to label all of my sides here. So what's that missing side? You're right, it's 3 long. But the actual y coordinate would be -3. Now, if I want to find my theta, I could find the inverse cosine of 4/5. But the problem is when I do that on my calculator, my inverse cosine of 4 divided by 5 is 36.8 degrees. It's about 37 degrees. And that is no way what that rotation is. That rotation is more than 37 degrees. Really, you haven't found theta at all. What you found here is theta prime. You found this angle is what you found. That's 37. Now, what does that make the rotation? This angle would be 360 degrees minus 37 degrees. My actual theta, not my theta prime, but that rotation is going to be 360 minus 37. The rotation is 323 degrees, about. So if this boom crane operator wanted to get to this point right here, he wouldn't just rotate 37 degrees, he would rotate 323 degrees to get to that load sitting right there. You have to think that back through in the end, all right? I've labeled the sides of my triangle. I've shown my rotation angle very carefully. It's in black right there. That's the theta. I've labeled it, and it's about 323. You try part C. Okay, I want to draw this angle in quadrant 3. So I need to rotate and stop someplace in quadrant 3. Now, the way I stop is to have a y coordinate of 24 and an x coordinate of 7. So I need to be a lot farther down than I am over when I rotate. This is 24 and that's 7. That's not really right. I mean, that's how long those sides are, but that's not the coordinates of this point. The coordinates of this point would be -7, -24. That would be the coordinates of this point. missing side 25 according to Pythagoras, right? So if I want my theta, I can do for my theta the inverse tangent of 24 over 7, but that won't be theta, that'll actually be theta prime. My reference angle, inverse tangent of 24 over 7, is about 74 degrees. That's my reference angle. That's this theta prime right in there. So what does that make theta, the actual rotation? If theta prime is 74, how much do you have to rotate from here to here in order to pick up that load right there? We'd need 180 plus 74 to get theta. 180 plus the 74. My theta, my rotation angle, is 254 degrees. And I've labeled all the sides of my triangle. I just think I ought to label this -7 and that -24, but 25 for the radius. As a last question, if I say that the sine of theta is -4 over 5 and it's in quadrant 4, which is negative, the 4, the 5, or both? Okay, in this case, remember this is y and that's r. If we're talking about in quadrant 4, your y coordinate can be negative, but your r can never be negative. R is always positive. So we can let y be -4 and r be +5, but it cannot be the case that y is +4 and r is -5. It also can't be the case that they're both negative, because then we wouldn't even have a negative ratio. So the correct answer is 4 is the one that's negative. Now, it's not always the shorter one that's negative, okay? That's not what you want to memorize. What's important is that r is always positive. R stands for the distance for the origin, so it's always positive. X and or y can be negative. And in quadrant 4, y is negative in a quadrant 4 rotation. We just really have to work on the difference between a reference angle versus a rotation angle. We're going to use theta whenever we talk about a rotation, and it will always be from the positive x-axis until the terminal ray, counterclockwise. And we're going to use theta prime notation for when we talk about a reference angle. So rotation angles always start on the positive x-axis, where reference angles can really start at any axis at all. But reference angles are always acute. Okay? They're between 0 and 90. They're acute angles, where rotation angles can definitely be larger than 90. Rotation angles could end in quadrant 2. That's larger than 90. They can end in quadrant 3. That rotation's larger than 90. They can end in quadrant 4. That rotation is larger than 90. Here's 90 degrees. Here's 180 degree rotation. There's 270 degree rotation, and there's 360 degree rotation or 0 rotation, depending on how you think about it, right? So remember that for rotation angles, they can be larger, can be more than 90 degrees, depending on what quadrant they end in. But reference angles are always acute because they're always the angle to the nearest x-axis. So I'm going to show here in green my reference angles. There's a reference angle, theta prime. There's the reference angle, theta prime. And there's the reference angle, theta prime. Those are all the rotations to the closest x-axis for each of those rotation angles.